Okay, so today will be our last lecture before our final presentation. So if you haven't signed up the permission form for the recording and release for your final presentation on next Thursday, please do so at your convenience. So today we're going to wrap up our lecture and by talking about the MCMC. Okay, so like we said in last time, the sampling methods are very important for statistical inference. The reason is that we want to sample parameter values from a posterior distribution Bayesian statistics so that we can use the sample parameter values to do Monte Carlo approximation to approximate the posterior mean, posterior variance, etc. So there's a question in the chat box. Do we have class on Tuesday? No, we don't. So this will be the last lecture because in the next week we have combined our two class time into one for the final presentation on Thursday. So on Thursday we're going to go from 3:30 to 6 p.m. to finish all the presentation at once. Okay. So coming back to the MCMC. So last time we talked about how to sample from a univariate distribution, which means that the distribution is for one-dimensional random variable. We talk about the simplest case where you know the CDF of the distribution. So in that case, you can just draw a sample from uniform 0 to 1, and then you want to convert those values into by doing F inverse, CDF inverse, so that the transform values will follow the distribution with CDFF. That's the simplest case. And if you recall, that's how we did with the liquid association in 2 lectures before. So we said that you need to transform your data into standard normal before applying liquid association. That's exactly the technique we use over there. And then we talk about 2 other approaches. One is the rejection sampling, which means that if your target distribution is difficult to sample from, especially when you don't know the normalization constant of the probability density function, or called PDF. So in that case, if you cannot really obtain the true or the exact PDF, you cannot get the CDF, so the first approach doesn't apply. Then what you can do is that if you can find an envelope density, which means that that density subject to a constant can cover your target density, and you can easily sample from that envelope density, then you can use rejection sampling. So you would just sample from the envelope density, and with every value you sampled, you have a certain probability of accepting it, and that probability depends on the ratio of your target density and the envelope density. And then we talk about importance sampling, which is different from rejection sampling in that you don't throw any values you sample, but you give them different weights depending on, again, the ratio between the target density and the envelope density, so that you can keep everything, but you just reweight the values so that after the reweighting, you can approximate the expectation of a random variable or a transform random variable from the target density, under the target density. Okay, then these are the things we talk about, the sampling approaches for univariate distribution. And then we move on to talk about Markov chain-based simulation or sampling. So this is what we call MCMC. So in MCMC, what's different is that you're not doing independent sampling from a distribution, no matter it's a target distribution or an envelope distribution. What you do here is to sample by following a Markov chain. In other words, what you do is that you need to specify a transition distribution, we write down here. So what you do is that given the current value you draw, you want to draw the next value by following the transition distribution. And the transition distribution has 2 arguments. One is the current value you put on after the conditioning, and the other is the value you want to draw. So this is exactly what the first order Markov chain is doing. Your next random variable just depends on the previous random variable for its distribution, and it doesn't depend on any other random variables before the previous random variable. Okay, so to achieve that, our goal is to find what we call the invariant distribution. So by invariant distribution, it means that once our marker chain grows, and enters equilibrium state, then in the equilibrium state, if you look at the distribution of any random variable in the chain, it will follow this invariant distribution. So in other words, you can just take the values, okay, the realizations of the random variables after the equilibrium, in the equilibrium state, as if they are an IID sample from this target distribution pi. So that's what we want to do. But we want to ensure a way to find a way that is the transition distribution, so we can grow the chain. And once we know the chain has been grown long enough, we are in the equilibrium state, and then we can take other values after that and use that as a sample from the target distribution. That's the basic idea of MCMC. So like I said, what we want to do is that given our target density, which is probably not normalized pi, to find the transition distribution, what we need to grow the chain, and then with the chain, we can start the sampling. Okay, so then the question is how to find the transition distribution given the target density. Do we have any questions about this part before we go into the technical detail? And after we introduce the algorithm, we will actually give you some concrete examples for you to see how it works. Okay, so the theoretical foundation for finding the transition distribution is this called detailed balance equation. So this is the definition of equilibrium. That means that given the current value is x, you get the next value equal to y. It's the same as given the current value is y, you get the next value as x. In other words, you have equilibrium between the two values x and y. Okay, so yeah, so then what we want to introduce here is what we call the famous Metropolis-Hasting algorithm. It's the foundation for the MCMC. And just for your information, I recently learned from a news in New York Times. It was about a female scientist who was the person who coded the first Metropolis-Hasting algorithm using computer. That was back in the 1960s, 70s, but her name was not included here. And Metropolis was the person who provided a computational resource. So I just learned that from that piece of news very recently. And people were memorizing that female scientist for her contribution. So if you're interested, you can check that out. This is available on the Wikipedia page for Metropolis-Hasting algorithm. So what we want to do, just to emphasize this again, is that we want to find the t given our pi. Okay, so clearly we don't know what's the t, but Metropolis-Hasting provides an interesting way of thinking, which is similar to rejection sampling. That is, we can just use whatever we can easily sample from to start with, and then modify that distribution to satisfy our need. Okay, so this is something we call a proposal distribution to start with. And the proposal density distribution must be something too easy to sample from. And it should be a distribution just like our transition distribution, in that it allows us to draw our next value given our current value. So for example, one thing that can first come to our mind is always the normal distribution, right? So we can define this proposal distribution, which we call Q, X, and Y, as the normal distribution as the density PDF of normal x1. So that means we use x as our center, the mean of our distribution, and we draw y as a value that surrounds x by following this normal density. So that means this density will take the form as 1 over root 2 pi exponential to the power y minus x squared over 2, right? So this is exactly the density of normal with x as the mean, 1 as the standard deviation. So if we do that, this is one way to go from value x to value y. But this density may not satisfy this detailed balance equation. But if we do just use this detailed balance equation, we may find that pi x times qxy may not be equal to pi y qyx. Otherwise, we're done. We can just use this q. But this is unlikely to happen. So we often will have this inequality. So then what do we do? So here, the Metropolis-Hasting algorithm is to say that, okay, whenever they're unequal, we must have one side bigger than the other side. So we can just simply assume that the left-hand side is bigger. If we have the pi x times qxy greater than pi y times qyx, how can you make it balance? The simple thing to think is that probably I just need to multiply a factor less than 1 to the left-hand side so that I can create an equation. Okay, so how do you do that? You can, the most obvious thing is that you can just define what we call this as a Fudge factor. And I can call that factor as alpha, x, and y. So if I do that, you see if I have alpha, x, and y equal to pi y times qyx divided by pi x times qx and y. Clearly, in this case, this is less than 1. Then you will be able to see, yeah, pi x qxy times alpha, x, and y will be equal to pi y qyx naturally, just by the definition of the Fudge factor. But now you see, on the left-hand side, we have 3 terms. The right-hand side only has 2 terms, right? That doesn't look symmetric to us. So then what we could do is that we could also say, okay, on the right-hand side, we have pi alpha yx. So we have complete symmetry. So whenever, it's just like on the right-hand side, we swap the x and y from the left-hand side. And if I want to achieve that, then I just need to define alpha yx equals 1. So if I have this and this, then I have this equation. Right, so you see, we're close to our detailed balance equation. On the left-hand side, we multiply by a factor less than 1. On the right-hand side, we multiply by a factor of 1. So this is the case when we have left-hand side greater than right-hand side. We could have the left-hand side less than the right-hand side, so that all the argument will carry over. You can see whenever I have this as less than, what happens is that this factor will become greater than 1. Okay? And then that's not so ideal for us because we want to have the factor no greater than 1. Then what do? We can actually easily address this problem by using this general definition. That is, to make this Fudge factor with a general formula, we could just define alpha, x, and y as the minimum of 2 things. One is the ratio, like we have here, pi y times qyx divided by pi x times qxy. The minimum of this ratio and 1. So that's what we can do for alpha, x, and y. And then this definition is in general because whenever we swap y and x, we are going to have alpha yx as the ratio. Now the numerator and denominator are swapped pi x qxy divided by pi y qyx 1. So then you can see in the previous case, when the left-hand side is greater than the right-hand side, alpha xy will be equal to the ratio, while alpha yx will be equal to 1. In the other case, when the left-hand side is less than the right-hand side, alpha x and y will be 1, while alpha yx will be the ratio. So that's why this general formula, this formula will give me a very interesting case. That is, only one of them, alpha xy or alpha yx, will get a value equal to 1, and the other will get a value less than 1. So that can help me satisfy this balance equation. Does that make sense to everyone? Yeah, so it's a very interesting construction of the fudge factor. So with this, then you see, we actually achieve what we want. So together, q, x, and y, and alpha x and y, this and this, give me the transition probability I need. So that means, or transition distribution I need. What this means is that, so given the current value x, I draw my y following q, x, and y, but I don't accept it for sure. I only accept it with probability alpha x and y. So that's just like what we do for under the rejection sampling. And so if alpha x and y is less than 1, I only accept it up to a probability. But when alpha x and y, yx is equal to 1, I accept it for sure. So the same idea as the rejection sampling. We modify our proposal density by multiplying a factor less than 1. So we can modify the density to be the transition density we need. Okay, so let me just give you a concrete example. So the algorithm works as follows. So we can just randomly start with x1. So initialize with x1. This is just some random value. Okay, and then we draw x2, the realization of the second variable in the Markov chain by following this density qx1 dot. Dot means that this is the argument, this is the density we want to draw from. So for example, I can say, okay, my x2 is just drawn from a normal distribution with x1 as the mean, 1 as the standard deviation, the example we give you above. Now with this x2, we want to decide whether we want to keep it or not. Then what we can do is that we draw z from, or I can say z2 from a Bernoulli, okay? And the Bernoulli will have a parameter equal to what we have here. So it will be pi x2 times q x2 x1 divided by pi x1 times q x1 x2. Okay, please note that the pi is what we know is the target density. We know up to a constant, and we want to sample from it. So we know how to do the calculation. And you see the magic here is that because we know pi up to a constant, and although we don't know that normalization constant to make pi a valid density, but once you do the ratio, that constant get canceled from the numerator and denominator. So you don't need to worry about that density, that constant at all. Okay, and because this ratio is less or equal than 1, so we can use this Bernoulli to draw Z2. And then if Z2 equals 1, we accept X2, okay? Otherwise, if Z2 equals 0, you set X2 equals to X1, which means that you don't accept your value. You just stay at your current value. And then no matter what, you have your X2, whether the new value or the old value. Following that, you draw X3 from the transition or proposed distribution with x2 as the current value. So for example, your x3 will be sampled from the normal density with x2 as the mean, 1 as a standard deviation, and then you draw z3, and so on. So you just do this continuously. With the current value, you draw next value, but the next value is not going to be accepted for sure. You only accept it based on a probability. That depends on this ratio. This is what we call Metropolis-Hasting. And you need to grow the chain long enough so that basically what you can see is that we call the mixing time, okay? So the mixing time is actually the number of iterations or the number of samplings before the Markov chain reaches equilibrium. I think people often set this mixing time to 1000. That's what's usually in practice. But how can you see this visually? Okay, so what you can do is that you can plot, say, your xi in the y-axis, the values you sampled, and you can each dimension of xi. Okay, so if your xi is multi-dimensional, you will just plot each dimension of xi in the y-axis. You plot your I, the iteration in the y-axis, or the sampling number in the x-axis. And if you see, okay, probably some values you have some value that don't change, which means that you don't accept any of the new values you draw, and then you can probably see the values change and change. But previously, in the earlier stage, the values are not so regular, okay? But later in the chain, you probably see very regular change in your value. So when you see pattern like that, for every dimension you draw of the sample you draw, then you can trust, okay, I'm in the equilibrium state because my values are alternating between the possible values in a quite free way. And then you can say, okay, I stop here. I take all the values after I draw after this point, and I'll treat those values as a random sample from my target density pi. That's what you do. Okay, that's the general Metropolis-Hasting algorithm. So you can think of it as a way of using Markov chain to do sample in combination with rejection sampling. Do you have questions? Okay, so the next thing I'm going to talk about, which is more widely used in bioinformatics algorithm, is called the Gibbs Sampler. And the Gibbs Sampler is specifically designed for a multivariate random variable, such as a random variate parameter in Bayesian modeling. So we will say that the random variable we want to sample from is m-dimensional. Okay, so x itself is m-dimensional, and we can actually write it out as x1 to xm. Okay, transpose. So this is an m-dimensional random vector. The reason I put the dimension in the superscript instead of the subscript is because we already use the subscript for the position in our Markov chain. So we don't want to confuse those two notations. So in other words, your Markov chain will look like this. So we will have the first random vector in the first time point or position. We call that x11 to x1n. Okay, and that will allow me to go to my second random vector x21 to x2n, and up to xn1 to xnn, to the next one, xn plus 1 to xn plus 1m, and so on. So you see, the chain is a chain of random vectors instead of one-dimensional random variables. Okay, that's the notation I want to clarify. And then Gibbs Sampler is a special case of Metropolis-Hasting, which give you a very nice transition probability, or also we can say the proposal distribution that will naturally satisfy the detailed balance equation. So you don't need to fudge it using a fudge factor like this. So you will have acceptance rate equal to 1. So this is a special case of Metropolis-Hasting algorithm by providing a proposal distribution with acceptance rate equal to 1. So you always accept the sample you draw next. So that gives us a very efficient way of growing the Markov chain and doing sampling. Okay, so what does it do? So the requirement is that for each dimension in your random vector, if you condition it on the other dimensions, you can easily sample that single dimension. Okay, so it is easy to sample from the distribution of, I call that xj, given all the other dimensions, and I call that x minus j, okay, for all j that goes from 1 to m. That means for every dimension in my random vector, if I know its conditional distribution given the other dimensions, if that distribution is easy to sample from, then I will just do that. So this is what I need for Gibbs Sampler. So for example, x minus 1 means the dimension starting from x2 to xm. Okay, this is what I mean by x minus 1. And x minus 2 means x1, x3 to xm. So I leave out the dimension I want to sample from. So we will see a concrete example very soon about how Gibbs Sampler exactly works. So with this, we will just continuously doing this sampling from the conditional distribution for every dimension. So what it means is that given for the algorithm, how it works is that we still do initialization for the first random vectors in realization. So we just call that x11 to x1m. We randomly set those m numbers. Okay, and then once we start our iteration, we will first sample for the second random vectors realization in the first dimension. We are going to sample it from the distribution of x1 given x minus 1. Okay, so I'm going to draw a value from this distribution, and for the x minus 1, I'm setting their values to what I have, to x1 minus 1. So this means that this is a random vector with m minus 1 dimensions, and I'm conditioning that it equals the realization I currently have with the first dimension removed. So this is just equal to x12 to x1m. So I want to sample from this distribution. And then I want to sample my x22. So I'm still in my second random vector. I'm sampling second dimension. And this is going to be sampled from the distribution of the second dimension, conditioning on that the other dimension is equal to, so now the first dimension becomes x21, and the third dimension becomes x13 and x14 up to x1m. So you see, I'm doing conditioning with the other values, but the first dimension is now updated in the previous step. And then I continue to do sampling for the third dimension. I call that x23. This is going to be sampled from the distribution of x3, the third dimension, conditioned on all the other dimensions. So this, I will use x21, x22, sorry, lowercase x22, the two values I got. The third dimension is going to be left out, right? Because it's the one we will sample from. And we have x14 up to x1m. Okay, so I'll continue to do that. Finally, I will update, or I will sample the m dimension from the distribution of xm, conditioning on x minus m. And now all the previous dimensions have been updated. So I will have x21 to x2m minus 1. Okay, so after m update, I finally draw the realization of my x2 in the marker chain. And then I will draw x31 similarly and go to x3m. So I will draw m times to get the third realization of my random vector. So that's how I grow the chain. So you see, to put them together, what I essentially have is the vector x1, which is equal to x11 to x1m, going to vector x2, which is equal to x21 to x2m, and going up to xn, which is also m-dimensional, xn1 to xnm, and go to xm plus 1, which is xm plus 1 to xm plus 1m, and so on. So this is how I grow the chain. So do we have questions for this part? So how we are doing the sampling in Gibbs Sampler. So if you don't have a concrete idea about how the conditional distribution look like, we're going to see that very soon. So you can defer your question until we do the real example. But no, you just need to know that for now, the Gibbs sampling is working by sampling dimension by dimension. In every step, you need to do m updates to fully update the m dimension before you go to the next step, go to the next time point in the marker chain. Okay, so the next thing I want to talk about is why the Gibbs sampler in this form is a special type of Metropolis-Hasting, and why do we have an acceptance rate of 1? You see that when I introduced this, we just keep going. We didn't reject any values we sampled. Okay, so to answer that question, we need to know what is our transition probability. It's actually following this one, okay? This is our transition. We are making transitions dimension by dimension. So you see that even though I write the chain as this, but essentially to go from here to here, I need to go through m updates. So essentially I need to decompose this into n transitions. And we are going to show you that for each of those m transitions, we are satisfying the detailed balance equation. So let's take a look. So to check that, we need to take a look at what's happening in this one step. Okay, so I'm going to go from the step xn to xn plus 1, so to give you this idea. So I'm going to say that, let's look at the transition of, let me see, probably I'll just look at this one. So for xn, let's say that I already have my first j minus 1 dimensions updated, okay? But starting from the jth dimension to the nth dimension, I'm staying at my current nth value. So the first j minus 1 have been updated. But starting from here, they are not updated yet. So in the next update, I'm going to go by changing xnj to xn plus 1j. Okay, and after that, I'm still at xnj plus 1 to xnm. And of course, before that, everything is at n plus 1 to xn plus 1 j minus 1. So you see, what I'm showing here is a local update where I change the jth dimension from the nth value to the n plus 1 value. Other things stay the same. So basically, you see here, if I call this as I just need a notation. If I call this as value x, this as value y for simplicity, okay, then you can see that what it actually is. So what is pi x times q xy in my detailed balance equation? It is actually the joint distribution of these things. So that is, I can write it as, I'll just write this as the joint distribution probability notation. I'm going to call that probability. I'll just call that. Okay, so, or probably I'll just stay with pi because pi is the thing I want to sample from. So I'll use pi with xn plus 1, 1 to xn plus 1 dimension j minus 1 xnj xn plus 1 xnj plus 1 to xnm. Okay, that's the joint density I want to sample from, and I'm evaluating it at my current value. And for the transition, you see what happens is that the jth dimension is changed, but the other dimensions are being conditional. So here the transition is essentially this distribution, okay? So I will call that distribution Pj to mean that it's the distribution for condition for dimension j of value. The value I draw, you see the value I draw is xn plus 1j. That's the value I draw. And what I'm conditional on is that I'm conditioning on the, what's that? So xn1, n plus 1, 1, to xn plus 1, j minus 1. After that, I have xnj plus 1 to xnm. So I'm conditioning on these other values to draw this particular value, and that's a conditional distribution. Okay, so you see what I'm having here is interesting. This is the joint distribution of all the m dimensions, and I'm having m minus 1 of them. So these, okay, so I want to say how this is clearer. These at j plus 1 is here, and these are also here. So they are actually in the condition. And what I have more is that here the xj, which is here, it's not in the condition, but that's okay. So you know, we always have the rule that is the marginal probability times the conditional probability will give us the joint probability. So that's just the fact of the probability theory. Probably to help you understand that, I'm going to drop the j. Yeah, I think I should drop the j to make you be clearer that this is just the conditional density. I'm getting the conditional density of the jth dimension, conditional on the remaining dimensions. But these remaining dimensions have their joint distribution in pi. So together, I can combine these two terms by having a larger joint density. So that will give me, okay, these things will get out of the conditioning, and I will have this here and also here. So what's left for me is that I'm going to have xn plus 1, 1 to xn plus 1 j minus 1. For the jth dimension, I'm going to have the x and j that comes down from here. And I'm going to have xn plus 1j, the next value that comes from here. And all the other things, xn j plus 1 to xn m. Okay, that's for the left-hand side. And similarly, for the right-hand side, I'm going to write it as pi y times qyx, which means that I'm going to jump from here to here. So now this is my current value, and I'm going to evaluate my target density on the current value. So I will write it as pi. So look at what's the definition of y. xn plus 1, 1 to xn plus 1j minus 1. The new value, xn plus 1j, xnj plus 1 to xnm. Okay, that's pi y. And for the transition, you see, other dimensions stay the same. What's only changed is that I'm now going to go from xm plus 1j back to xnj. So it's still the conditional distribution of dimension j, but now the value I'm going to draw is not xnj, it's not xm plus 1j, but xnj. This is the value I draw because I'm going from here to here. And the conditional values are still the remaining dimensions, and they stay the same. So I have xm plus 1, 1j, xm plus 1, 1, to xm plus 1j minus 1, xnj plus 1 to xnm. Okay, so same argument carries. I'm going to combine this term with this term to get a big joint density. So you see, if I do the combination, these things will go down. xm plus 1, 1 to xm plus 1j minus 1. And xn plus 1j will go down. And I'll also have a thing from this part. So that will give me xnj, yes, that will give me xnj and all the remaining things in the condition. That's xn plus 1j, sorry, xnj plus 1 to xnm. Okay, finally, you see that these two things are essentially the same. Left-hand side, right-hand side. Here I have those two. Here I have those two as well. It's just that they are in a different order because by how I write it. But essentially, this is the same joint density as this one. So that's why we naturally have the details balance equation satisfied by this proposal distribution. So that's why Gibbs Sampler gave us the acceptance rate of 1. We don't need a Fudge factor to adjust it, so we can accept every sample we draw. Does that make sense? And the fact is that we're using the conditional distribution of one dimension given the other dimensions as our proposal distribution for transitioning. Okay, so now let's take a look at one good example. I think I'm going to do this example first before we do the other example. Okay, so I'm going to first do an interesting example so you see why Gibbs Sampler is so useful. Okay, so let's say that we want to draw from this target density with 2 dimensions. So here I just refer to the 2 dimensions as x and y. So this density, the target PDF, has the form that it is proportional to n choose x, y to the power of x plus alpha minus 1 times 1 minus y to the power m minus x plus beta. I think it's minus 1. Yeah. So what this means is that here the x is taking values from integer values from 0 to n, up to n. N is an integer, while y is between 0 and 1. So these are the two domains for the 2 dimensions. Okay, so if I ask you to draw, and also I want to say that alpha is positive, beta is positive, and n is positive integer. Okay, so I'll just say it's the positive integer like this. So given these conditions on the 3 parameters n, alpha, and beta, and also the domain for our x and y. So if I want to ask you to draw from this distribution, it's not so obvious. How would you sample from this distribution? It's not a well-defined, or it's not a common distribution. But if you recognize this form, if you are familiar with what we call the binomial probability mass function and also the beta density function, then you can actually recognize this model. So it has some similar form we have seen before. So that is, if we conditional on y, so given this density, okay, so this is just the joint density of a random vector x and y that follows. It's difficult to sample from. But if you look at this conditional density, if I just set y equals to lowercase y and just want to sample x, then you see, given this, it's actually something we are quite familiar with, right? This is just a binomial. So basically, we can say that if we have this y set to be this, then this is proportional to, I can get rid of the things that has nothing to do with x. So for example, y to the power alpha is a constant now. It has nothing to do with my x. So I can just keep the term involving x. So this will give me n choose x times y to the power x times 1 minus y to the power n minus x. Because other terms are not involving x, I can regard them as constants. And this will tell me that I can say, okay, x given y equals y is just following binomial with a total n and the probability as y. So I can draw my x using this distribution. That's one conditional distribution. And then if I look at the other way, what is the conditional distribution of y given that x takes the value small x? So with that, when x is set, then the first constant n choose x can be gone. It's a constant. And we can just keep the terms that involve y. So we can see that this is proportional to y to the power x plus alpha minus 1 times 1 minus y to the power n minus x plus beta minus 1. And we can recognize this is the density of a beta distribution. So we can say that for conditional on x equals small x, the conditional distribution of y is actually beta, with the 2 parameters as x plus alpha, and the other one is n minus x plus beta. Okay, so these two, binomial and beta, are common distributions from which we can easily sample. So we're done. So we have the foundation for what we need in Gibbs Sampler. So essentially what we do is that in the Gibbs Sampler, what we have is that we initialize our x. We call that x1 and y1, okay, randomly. And then we draw x2 just from this binomial distribution with total n, and y is set to y1, okay? And next, we draw our Y2 from a beta distribution with x set to x2. So we have x2 plus alpha and minus x2 plus beta. That's what we do. And then we continue. We draw x3 from binomial with total n parameter probability y2. And then y3 is going to be drawn from beta with two parameters as x3 plus alpha and minus x3 plus beta, and so on. So you see, you're just alternating this procedure by updating the x and by updating the y. And then you can check, okay, all the values you have drawn, right? So you can plot this. You can plot this as your n, and this is as your xn. And you can also do this plotting for yn. So you can see how the values you draw change as your iteration goes, as you grow your marker chain. So if you see that the values are alternating at a steady state, which means that your chain has entered equilibrium, then you can pick the values after that for your x and the y. That will be the sample you draw from this target density pattern. Okay, so this is just a simple illustration of why Gibbs sampler can be so useful, especially in Bayesian statistics. When we use like a likelihood, we will assume a likelihood based on a common distribution. And we also assume a conjugate prior, which is another common distribution. So in that case, your posterior is usually in the same family as the conjugate prior. So it's easy to sample from. So you're done. You don't worry about that. But when the prior is not conjugate, but it's another common distribution, so you multiply that prior with a likelihood, you may get a posterior that's not easy to sample from, but it can give you some nice conditional distribution that you can easily sample from. So that's the case when you can apply the Gibbs sampler. Okay, so I can actually show you something which is related to the second example. It's related to what you have done in your homework before, the Gaussian mixture model. You have fit that model using the EM algorithm, right? Using the latent variable formulation. So you can do that. But here we can offer you another perspective for solving the same problem. But here we're not interested in doing, so yeah, maybe let's talk about that. So as I talk about that, you'll see what I mean better. So we call this data augmentation. This is a technique in Bayesian statistics, which means that you create a latent variable to make the sampling easier. A latent variable to be sampled together with parameters in Bayesian inference. So we know that in Bayesian inference, what we want to do is to sample from a complicated posterior. So what we draw are the values of parameters. But we may want to add a latent variable as missing data and sample that together with the parameters to make the sampling parameters easier. And this is the case. So we assume that our data, so this is our data's likelihood, okay? So we assume that the data will follow a Gaussian mixture model. So I made the mistake. I shouldn't say the likelihood of data. I should say the likelihood, this is the data generation we are going to use for writing down a likelihood of parameters. That's the accurate way of saying it. So for this one, we can say, okay, the Gaussian mixture model with PDF, as we can write the PDF as fx equal to, let's say it has k components. So let's say k, small k go from 1 to big K. We have the pi k, phi kx. Okay, so each component here is one Gaussian distribution density and we add them up using the weights. And here, of course, the weights must sum up to 1. Okay, that's a valid Gaussian mixture model. And our data comes from this density. And this is the data generation. So let's say that here we have priors. So for simplicity, I would just say, okay, phi kx, this particular density for the kth component has the form 1 over root 2 pi exponential to the power 2 x minus mu k squared. So in other words, this phi kx, this is the PDF of this normal with mean mu k, standard deviation 1. That's its PDF. So for simplicity here, we assume all the components in the Gaussian mixture model to have unit variance. So we only worry about the mean, just for simplicity. Okay, so here we are using a Bayesian framework. So we have prior for the mean. So here we just assume, okay, for the capital K component, we have mu1 to mu k. For simplicity, we assume that they are IID from a prior, and the prior has mean 0 with the variance equal to mu. Or probably I just say mu squared to make the notation more familiar. So you see that this is a commonly used prior in statistics, and what we call this as shrinkage estimation. Sometimes you will see the term here. So shrinkage estimation is a term people use in frequency statistics. So what I mean is that they are interested in estimating mu1 to mu k, but they realize that we don't have many data points, so we don't afford to estimate capital K parameters, which are too many. So what they do is that they borrow the Bayesian framework by assuming a prior. So as a result, the Bayesian estimator you will get from the posterior mean, okay, will be a weighted sum of what you get from the data and what you have from the prior. So you're basically going to shrink the estimator or the estimated mu1 hat to mu k hat closer to the mean. So it's a way to make their variance smaller, because like I said, the issue is that you don't have enough data points. So shrinkage estimation is a way to make your estimator closer to the mean so that those estimators do not vary too much as your data change, as you change your sample. So it's a way to reduce the sampling variance of your estimator, but by creating a bias. So it's not unbiased because you are arbitrarily shrinking them to the mean, to the 0, sorry. So if this is something you don't understand for now, it's totally fine. I'm just mentioning this for some of our a little more advanced students who have heard of this term. But if this is something totally new to you, just ignore it. Okay, so that's the prior. And then we are going to write down the posterior. So that will be, if I have data, say if I have data coming from this mixture, so I'll write the data as x1 to xn. That's the IID data coming from this F, okay? So if I want to do Bayesian, what I need is to derive the distribution of mu1 to mu k. Their joint distribution given my data x1 to xn. That's the distribution I want to have. And with that distribution, I can talk about posterior mean. So then I will need to call, say, I will have mu1 hat to be the posterior mean of, say, mu1 given x1 to xn. And then mu hat k to be the expectation of mu k given x1 to xn. That's what I want to have. Okay, this is what I want to achieve using the Bayesian inference. But of course, I need the posterior distribution. And clearly, you see, it can be quite complicated because what I need is that the posterior, okay, the posterior here, I know it's going to be proportional to the likelihood times the prior. But the likelihood is super complicated. You see, the likelihood is going to be I go from 1 to n times the product of the sum k from 1 to capital K, pi k, phi k, xi. You see, I'm going to have this sum inside the product, and then I'm going to multiply this by the joint distribution. I'll just write this as P mu K, and with the product K from 1 to capital K. So this is going to come from the prior. Prior is going to be here, but the likelihood part, this product, is going to be very complicated. So it's not easy to just get the posterior directly. Then that's why we need data augmentation. So how data augmentation works is that you assume is to introduce Z1 to ZK, Z1 to Zn, which you don't observe. But you assume these are the latent memberships of your X1 to Xn. Okay, and you are actually going to assume these memberships are IID from a multinomial distribution, okay, with a total 1. We only sample once, and the probability for K classes is going to be pi 1 to pi K. So you are going to sample from this multinomial, which means that you are going to draw one of the K classes with different probabilities specified by pi 1 to pi K. So with this, then your model becomes hierarchical. That is, I first draw Zi. So the new model, which is equivalent to the mixture model, but it's now hierarchical, is that you are going to draw Zi from this multinomial. Okay, I'm just going to write it quickly with these probabilities. And then given the Zi, I'm going to draw Xi. So Xi given the Zi is going to come from the normal distribution with the mean as the mu with Zi there, because Zi is going to be 1 to K. So given whatever Zi is, I'm going to draw from that distribution with that mean and standard deviation. That's the same. So the way to draw data in this way is equivalent to say I draw data from the Gaussian mixture model. Okay, and then you see I introduce these latent variables which I don't observe. But what's nice is that I can sample Zi together, Z1 to Zn together with my mu1 to mu k. That's super nice. So this is another application of the Gibbs sampler. So basically what we do is like this. So once it's just very similar to our EM algorithm, but it's a different perspective. So here what we want to do is that we just say, let me just write down the algorithm so it's clearer for you. So what we do first is that we randomly initialize mu1. I will say I'll cut them 0 here. Okay, mu1 to mu k0. I randomly initialize them. And then what I'm going to do is that I am going to draw my Zi, sample Zi, given those mu1, 0 to mu k0, which is actually possible. So I'm not going to derive this distribution here, but it's still going to be a multinomial, except that here in the new multinomial, I am going to change these parameters to be the new parameters. Probably I should just write it as pi or I should say, sorry, my bad. I should say pi 1, 0. Yeah, I need those. And pi k 0. Okay, so okay, I'm going to call this as together. This thing as my parameter, I call that theta 0. So then I'm going to sample my zi given the current parameter value theta 0 from this multinomial. Okay. So I do that for z1 to zn. So IID for all of them. And then what I'm going to do is that I will update my parameters. So the mu1, the mu1, 1, okay, let's just make this example, is going to be sampled from its posterior, okay? But the posterior is not going to be this posterior we have here. This is going to be the posterior mu1 conditioning on x1 to xn, our data, and as well as our sampled latent variables, z1, I call that 1, z1, 1 to zn1. Okay, so given that it's easier for me to compute to get this posterior, given the latent variables, that's the key. So I can do that, and also I can do that sampling for pi. Okay, pi 1, I'm going to sample from the distribution of pi 1 given the data as well. So this allows me to update all my parameters, and then given the updated parameters, I'm going to sample my latent variables again. So it's just a way, this data augmentation is a way to make the posterior easier by having the parameter condition to be conditional, not just on our observed data, but also on our latent data. So we can have a simpler form of posterior that can allow us to sample the parameters and the latent variables together, like in the Gibbs sampling way. And this has been, there was a theoretical paper in 1980s to prove that using the data augmentation by introducing latent variables to be sampled together with parameters will not change the distribution of the parameter value sampled. So in other words, if you just keep the parameter values, they still follow the original posterior you want to sample from. That's very important, and that's super nice. So just the take-home message is that in Bayesian statistics, people often use this data augmentation to introduce latent variables that you don't observe, but that can make the model easier to write down and make the posterior easier to derive. So that's just the take-home message. And the idea is quite similar to EM algorithm, which also introduced the latent variable for maximizing the likelihood. That's the likelihood over there. But here we work on posterior. And sometimes in bioinformatics paper, I want to say there is some ambiguous views about likelihood and posterior. So so after this class, I hope that when you read it, you have a better idea about what these papers are talking about. So when they talk about posterior, they are treating parameters as random variables, and they're treating your data as conditional, as being conditional in the posterior. But when they talk about likelihood, there should be no prior, or it is equivalent to the Bayesian posterior when you assume the prior is just flat, it's proportional to 1. So that's how you consider likelihood. And if you don't see that the description there is actually aligned with this concept, then probably you should question the quality of that paper. Yeah, so I just think after this class, hopefully you will get better understanding of those statistical concepts. And if you don't, I think it's good that you can come to my office hour to clarify your confusion after you solve your homework problems. And I don't expect everyone to be able to develop methods, right? This is just too short as a class. And it's not possible to have the ability to develop your new method just after taking this class. But still, I hope that it's better, this class will be useful for you to understand the method section of some bioinformatics papers if they use statistical methods. That's my hope. Okay, so that's all. That's everything I want to say for this class. And if you have any questions, you can stay And also you have the questions about your upcoming presentations next week, next Thursday afternoon, or the final project paper, you can also stay in the Zoom and ask your question. And okay, so thank you everyone, and I hope you can complete the course evaluation at your convenience.